Okay, so this is inference about population distributions, and we're going to introduce the t-test, where the big difference between the z-test and the t-test is slightly the table. Um, this is a small jump in the z to t. That's a very small jump. We're going to incorporate more things with tests, but the key with difference with the t-test is we do not need to know the population standard deviation. We can use the sample standard deviation, which if we have the data is always very easy to calculate. So looking at this, um, it has to be a sample distribute, a simple random sample, and your population, which is usually your population of means, again, has to follow a roughly normal distribution. The t-test happens to be more resistant to the non-normality than the z, which is a plus. Oh, okay, I gotta pause and fix my pen. Okay, the standard error, and I've referenced this a little bit by name, and it probably wasn't technically correct. The standard error is the sample standard deviation divided by square root of n. And we've been using standard deviation divided by square root of n with the population, but we haven't actually been doing that correctly. Well, that with the population, that's not technically the standard error. Sigma over square root of n. S over square root of n is the standard error. Um, here's your z formula. That's what we've been doing. Probably written more like this. We're going to adjust it to be x bar minus mu over s over square root of n. And that's going to give us the t distribution. Okay, or the t value that we'll look up in a t table. The t table itself only gives us positive cases and it reads off the tail. So the z distribution, the standard normal curve, is always to the left side. Well, the t, which is pretty similar, actually gives you the upper tail. And it's going to, if you need lower tail, it's the same value. The symmetry is an important piece. Okay, there is one other piece to the t distribution called the degrees of freedom. Okay, the degrees of freedom on the t distribution is simply n minus 1. I don't know why it's called degrees of freedom. As the t distribution, as n goes to infinity, the t distribution goes like a limit to the z distribution. So when you get super large sample sizes, the t is basically the same as the z. It starts to not matter. But looking at this, we're mostly going to be doing this with the calculator, and I'm going to show you how to do things with the calculator. So if you're looking at this distribution, the t with 2 degrees of freedom, a little bit wider, more spread out. With 9, it's starting to approach very closely the standard normal or the z distribution, the solid line being the z. So using the t-table, and then I'm going to show you how to do this all on your calculator too. And the z is done pretty much the same way. So what critical value t star from the tc would we use for distribution with 18 degrees of freedom having a probability of 0.9 to the left of t? So I go to my t-table. 18 degrees of freedom. I need to be able to see this. And you're going to see that the t distribution is always to the left here and the probability. So 0.9 to the left means 0.10 in the tail. Okay, I can see it all on here. So I'm looking at this column, I'm looking at 18 degrees of freedom, and my value T star equals 1.330. So instead of looking at it more specifically, the T table only gives us some of the commonly needed ones. It doesn't give us nearly the detail of the Z table, but it gives us enough detail. Doing this on your calculator, which is going to be important because you don't have a table on your test. Menu. You can get it either under distributions, either under statistics or under probability. And we are either looking at a TCDF or an inverse T. So TCDF, your lower bound, your upper bound, degrees of freedom, 18. I think that's right. No. Maybe my upper bound's probably 0.9, actually. Distributions is both under probability. They're the same. Maybe I probably have to use inverse T for this one. I'm looking at the table backwards. Inverse T area 0.9. Degrees of freedom 18. Is it 0.9 or is it about 0.1? There it is. So 0.9 to the left. Inverse T is going to look up and give me the T value. If I have a T value, the TCDF will give me a P value, and we'll use that potentially in the future. But for the most part, we're just going to use the table to look things up. Well, and we'll use inverse T if you need to show the calculation by hand. Again, for the most part, we're going to do all these calculations with T interval or stats test, t-test. And we'll also be getting 2 samples in the next lesson. So using the t-table, relatively straightforward. Again, degrees of freedom. So now suppose we have a 95% confidence interval. So this is getting a little trickier. 95% confidence interval gives me a tail on both sides of 2.5% or 0.025. With sample size 12, that means degrees of freedom equals 12 minus 1 or 11. So my t-table, I want to look up this boundary. So I need a 0.25. Actually, we'll do this one on the calculator and then I'll show it to you on the table. So this is an inverse T. Menu, probability, distributions, inverse T. Now that's TCDF. Menu, 5, inverse T. Area. So to the 0.025 to the left, 0.975. Degrees of freedom 11. 2.2 is my T value. If I choose instead to look that up in the T table, I look at my degrees of freedom line. My T table is getting the tail. Your inverse is the other side. 0.025, 2.201. Same thing I got on the calculator. But see how this little sketch of a normal curve becomes very helpful. Without the sketch of a normal curve, it sometimes becomes difficult to figure these out. So T confidence interval. Guess what? It's basically the same as the Z confidence interval. X bar, except we're using a T star instead of a Z star, and this is an S. These are the two things that changed, minor change. Um, Using a t-test. Um, Again, here's the formula. We are using x bar minus our assumed mu, and we're using the sample standard deviation. Again, we'll run most of these just calculating them on the calculator because it can do all of them for us nicely, easily, and quickly. So, auto pollution. Environmentalists, government officials, and vehicle manufacturers are interested in studying pollution. One of the major pollutions of hydrocarbons and nitrous oxides are NRX. So, the amount of NRX emitted by light duty engines in grams per mile. So, here we've got all this data. Construct a 95% confidence interval. So, studying the auto exhaust emissions produced by motor vehicles. So, this is a sample of light duty engines. We're looking for the average nitrogen oxides or NOx levels produced by light-duty engines of the same type. And that is our population of interest is all these light-duty engines. My appropriate inference procedures is a confidence interval. And to do this, I need to enter all of these into my calculator. So I'm going to start a new document, and I'm going to, don't want to save, add a list in spreadsheets. Okay, let me grab a book to look at. My data is on page 623. And I'm just going to label my column NOx. One, 2, 4, 6, 8, 10, 12. I am missing one piece of data. I'm going to look at my first row. I'm missing a 1.24. Luckily, this data, the order doesn't matter, so I'm just going to put the one I'm missing right in. So it's helpful to count and make sure you hit at the right number at the end of a line. There's 12 for each one, so 12, 24. This one should end at 36. Doesn't guarantee you get them all right, but it's a helpful checkpoint. 0.051 is definitely not right. Oops. I'm one short. I missed one. 0.94. Okay, I missed 1.51. And it's nice that I don't need to reorder this. So now that I've got all my data in the list, I'm going to, well, I need to check my assumptions. This says it comes from an SRS. So point one checked. Now to check normality, I don't really need to check normality. This is 46 points of data. The means will be normal. But for the heck of it, I'm going to show you how to check normality. Data and statistics. That looks approximately normal based on the dot plot. I could turn this into a histogram by doing histogram. That's plenty normal. With 40 or more, plenty normal. This one potential outlier is no big deal. Or I could do a normal probability plot, which would probably be my choice. Plenty close with data size of 40. This would be plenty close with data size of 20. But probably actually close enough with 10. With 40, I didn't really need to check, but I think it was a good practice to go through checking. So now I'm going to add a calculator. I'm going to do menu, statistics, confidence intervals. Instead of choosing a Z interval, I'm going to choose a T interval. My input method is data. If it had given me the mean, standard deviation, etc., I'd choose stats, and I would just enter them. My list is NOx. Frequency list, you're going to leave at 1, I think, always. Confidence level, it says 95%, 0.95. So my confidence interval is my true mean of NOx levels for all light duty engines is 1.18 to 1.47. So I've done my calculation. I've got my interval. I must make my conclusion. Interpreting in the context of the problem, we are 95% confident that the true mean level of nitrogen oxides emitted by this type of light duty engine is between 1.185, they want one more decimal than I did, and 1.472. This is grams per mile. It is important to give in your conclusion, give the units. Must be in context always, 100% of the time. So again, I got those values. Important things that you might want to write down on an IB test. Yes, C up or C lower. Don't write them down like that. Write them in interval notation, like this. You can probably do 3 sig figs because this is IB. They like 3 sig figs. They usually say that's 20. It gives you your mean. It gives you your standard deviation and degrees of freedom. You probably didn't need help getting degrees of freedom, but there it is. Okay. And so you can give these important pieces of data to show. You can even write out if you want, T equals 1.33 minus, no, I wait. It does not give me the T star value. So I guess it'd be hard you'd have to find the T star value. But you could find your T star value, fill it in, the minus 0.484 over square root of 46. This really shows your understanding of the work and will definitely mean you're going to get all the points. but I strongly encourage you to do the actual calculation on your calculator. Because you need to calculate the standard deviation anyways. They probably won't give you that large of a sample size on an IB test. So significance for mu when sigma is unknown. So cola makers test new recipes for loss of sweetness. Trained taste testers rate the sweetness before and after storage. Here are the sweetness losses. So this is how much this one says it lost 2 points on their scale. This one says it lost 0.4, this one 0.7. 2. This one, according to theirs, gained 0.4. Now, keep in mind, a couple months apart, you're going to get some variability. This one lost 2.2, gained 1.3. Is this good evidence that the cola lost sweetness? So, this is essentially a matched pairs, but they gave you the matched pairs data. So we're going to start with identify our population of interest. H naught. Population of interest is the sweetness loss for storage of this cola with artificial sweetener. Mu equals 0. We assume there's no sweetness loss. Always assume the no change case. Mu is greater than 0. This cola did lose sweetness when it was stored. Okay? Notice that when they gave this, they wrote out these things. You probably don't have to, but if you want to give a good conclusion and get the conclusion points, this really helps. Okay, choose the inference procedure. We're doing a t-test. We are going to verify the conditions. We're willing to treat our 10 tasters and their sampling as an SRS to draw conclusions. In general, we assume that their ratings they're trained in how to rate, but the variability in their ratings for trained tasters will be random. We're willing to assume that. So step 1, step 2, SRS, check. Now we got to assess normality. You cannot just say check on this. You need to actually discuss why you are willing, because it does not say that it is an SRS. You have to be willing to say that you will treat it as an SRS. Okay, I'm going to clear a few things out. The data for entering it into your calculator is on page 624 in the book. So I'm going to just start a new document, not saving that one. So I'm going to call it SW for sweetness or sweetness loss. I'm going to enter all the values. I don't know the data of how this test was conducted, so I can't assess its validity or any part like that. But we're going to assume it was conducted correctly and just run the stats. If those were not conducted correctly, all the stats we run will be meaningless. So the next thing I need to check is normality. This is only 10, so I need some level of normality. With 10, unless there's extreme deviations from normality, oh, this is probably not extreme. Doesn't look like super extreme outliers. I'm going to check it with the normal probability plot. Those aren't extreme outliers. Normality. I'm going to need to show maybe a sketch of this plot. With sample size 10, there's no extreme variations. So then you are going to need to show the plot and say no extreme variations, extreme outliers. So I'm willing to accept that this data is normal enough. Okay, and now I'm going to add a calculator screen and run a t-test. So I go statistics. I have to go to statistics here. I don't want distributions. I want a t-test. This is a one sample t-test. My input is data. My mu naught, I assumed 0. My list was SW. My alternative hypothesis was a mu is greater than 0 or mu is greater than mu naught, which was 0. So I'm comparing mu naught to what I entered for 0. That's what I had up the list. I hit enter. It gives me wonderful things that I should write out. So in my step 3, I should write out my t-value. I should write out my degrees of freedom. Probably should write out my x-bar and my standard deviation. And definitely my p-value. My p-value is 0.012. So I have about a 1.2% chance. So interpret my results. A p-value this low gives me quite strong evidence. So I could say I have a probability of 0.0122 or a 1.22% chance that this great of a variation occurred by random chance. So I am rejecting my H naught and concluding my HA, which means that the cola did lose sweetness during storage. Okay. Make sure to, you can give it in terms of reject H naught, conclude HA, but then you must put it in the context of the problem as well. Putting it in the context of the problem, really important. Okay, our next example involves some fluorescence and learning. And the question is going to be, does having a nice smell help you learn better? So this is going to be a matched pairs experiment. We're going to compare the response to one of the two treatments in a matched pairs. So we hear that listening to Mozart improves students' performance, and this was definitely believed at the time. Perhaps having pleasant odors will have a similar effect. They did this with 21 subjects, worked on a paper and pencil maze while wearing a mask. The mask was either unscented or carried a floral scent. The response variable is the average time on 3 trials. Each subject worked the maze with both masks in random order. So they randomized whether they did the maze with which scent they had first, no scent or randomized scent, because the more times you do it, probably the better you get at it. But does it make a difference and help? So we have all of this data. Okay. The key thing here is the difference column. We don't know, this one with having a negative difference probably did scented first and then unscented. But we could assume that maybe there's a difference because even though they did scented first, it didn't make as, it helped them be better and they didn't go as much faster. So the slower times are probably scented, and because it's randomized, you should have half that are faster and half that are slower. Okay. So identify the population of interest. Population of interest is people's ability to learn with, or does, it's people in general. And does, what we're interested in is, does having a floral scent significantly help people perform better on a maze test? We would probably want to generalize this to everything, but it's important that in our test results to only conclude what we actually tested. Okay? Now, we write our H naught. People perform H naught. There is no difference. And you could say this as sometimes the last one they called it mu diff, or the difference is 0. The difference is greater than 0. We assume that having a nice selling cent wouldn't make it worse. That's an assumption. Seems like a reasonable one. We're not going to give a nice selling cent probably if it doesn't make it better. So choosing the appropriate inference procedures and verifying the conditions using the selected procedures. We do not know the standard deviation or the population differences. So we do not know so we have to use T. The data comes from a randomized matched pairs experiment, which randomized matched pairs qualifies as an SRS. And so you're going to say randomized matched pairs, SRS check. Okay. We're looking for normality. This looks approximately normal with sample size 20. It is plenty normal, or sample size 21. It is plenty normal to meet the normality condition. Okay, they say a stem plot. They show the stem plot. Says the distribution is symmetric and appears reasonably normal in shape. We have no reason to question the normality of population of differences. And you could say we have no reason to question the normality of differences with sample size 21. Okay, the central limit theorem kind of gives us that. If the conditions are met, we're going to carry out the inference. And I don't feel like entering the data in the calculator, so I'm going to take these values. Now I'm going to show you putting it in with data. And I'm going to write my values down so I can see them clearly. That's 12.54. So I'll go to the calculator. I'll run my test. Menu, statistics, stat test, t-test. This time I'm going to choose stats. X bar, mu naught is assumed to be 0. X bar, 0.9567. SX 12.5479. N is 21. And again, we're looking at it this one-tailed. Get those out of the way. And we get a p-value of 0.36. So there's okay, we got T of 0.034, degrees of freedom 20. Writing those down. Make sure to write that down in your conclusions. With a p-value of 0.36, the data does not support the claim that fluorescence improved performance. I would fail to reject, and it's important to say that I would in this way. I would fail to reject H naught or conclude HA. Notice they do not say the data says it doesn't. The data does not support the claim. Okay? It doesn't say it doesn't improve. It just says our data does not support the claim that it does improve. The average improvement is small, just 0.96 seconds over 50 seconds in the average subject took when wearing the scented mask. The small improvement is not statistically significant. Okay? So don't bother, according to this test, taking floral scents or nice scents when you study, unless you're just doing it because you want to. But it probably won't increase your score. Looking at some of these things, this is the data from an output from what's called a program called Minitab. This will show up in the book a little bit. Here's your mean difference, and standard deviation of difference. Those are important. When it puts it in the t-test, we get a test statistic. That's the t-value, is t-stat. One-tailed p-value. So this one-tailed, that was what we were interested in because it was mu is greater than 0. That would be this one-tailed. Your p-value 0.36. If it was mu is not equal to, that's a two-tailed. And that's exactly twice that one-tailed p-value. Okay. Either way, a 36.5% chance that it was simply random variation is going to lead me to never conclude this being useful. It's important, though, to note being able to read it out of here. There's a lot of extra stuff. Pearson correlation, hypothesized mean difference. I guess we entered that one. Observations, mean variance, all these things don't affect it. So please don't take those into account. Only look for the useful things in these stats outputs. So again, is caffeine dependence real? So a couple of different things. We've got a couple pieces of data here. They've got data on depression score with caffeine or the placebo, and data on heart rate with caffeine or the placebo. Or I think beats is actually beats per minute of tapping. Okay. And we are interested in whether being deprived of caffeine affects these outcomes. We're going to construct a 90% confidence interval for the mean change. Okay, we're going to do this one on the calculator. We'll actually do it. The values show up on page 632 in your book. Our population of interest is, we're drawing conclusions about people who are caffeine dependent. It's not the general population in general, it's people with caffeine dependence and what happens to them if they're deprived of caffeine. So they were given either a caffeine pill or a placebo pill and not allowed to drink any other caffeine. So we're going to choose the appropriate inference procedures and verify the conditions. So we're looking at mu difference or mu placebo minus caffeine, and we're going to calculate a confidence interval. First thing I need to do is enter the data into two columns on the calculator. So I'm just going to start a new one. Half. And we're going to go placebo minus. So this is going to be, it's important the order we talk about our scores in. And they're going to make a positive difference. So they did placebo minus caffeine. It appears that there would be a positive difference. The bottom one, I'm not sure if they're caffeine dependent or they're just not prone to depression. Important thing here, we need to make a difference column because we're going to run all of our data on the difference. And in this, we can do placebo. And it's important that we specify. We just want it to be positive, so we did placebo minus caffeine instead of caffeine minus placebo. And yeah, one of them's negative. That's kind of normal. So we must test for normality. We're going to test for normality. If you look in the book, they did a split stem chart. So to test for no, so we have it's a randomized matched pairs. We're going to assume it's randomized. I guess it doesn't specify. Data comes from, this is probably not the case we may have trouble generalizing this to the population of caffeine-dependent people. Usually you can't get randomized people. If they did randomize which order they took which pill, you might be able to have more generalization. But with experiments, it is hard to get true SRSs. Like, this might be a little bit of trouble, but we're going to keep going anyways. And we're then going to look for normality in the distribution of placebo minus caffeine. So we're looking for the distribution in difference. They make a stem plot. I probably would have done a histogram or normal probability plot. Most likely. Would be, this isn't too non-normal, no extreme outliers with sample size of 11. That's close enough for T procedures because it starts to get normal pretty quickly with means based on the central limit theorem. Okay, let's run our test. So we're going to add without having that stem and leaf plot made, I would have added a data and statistics and looked at that. But since it was already made for me, I'm just going to use the one that was in the book. Stats, I'm going to run a stats test, a t-test on data. I assume the difference was 0. I'm not running a test, I'm running a confidence interval. It asked me to make a confidence interval, so I will make a confidence interval. Oops. I accidentally deleted my page. Menu, statistics, confidence interval, t-interval, data. I must do the one that's called difference. It asked me for a 90%, so okay. I get to type this, 0.9. And my upper and lower, 3.58. 11.1. So I can conclude that my mean difference in my caffeine-dependent population is going to be somewhere between 3.58 and 11.1 on this depression score, Beck depression inventory, when they are taking a placebo versus taking a caffeine pill. What is that? This study provides evidence that withholding caffeine from a caffeine-dependent individuals may lead to depression. It's important not to draw too strong of conclusions, but it is important. You can draw some conclusions. Yes, it wasn't a perfect SRS. It probably wasn't a perfect study because they're really hard to do. As we studied in TOK, you study the different difficulties with the human sciences and how hard these assumptions are to make. Okay, we're going to talk about robustness of the T procedures. And what robustness means is how resistant is it to variations? The T procedures in general are very robust. Outliers have an effect, but it's not too great of an effect. Okay, we're going to skip over that example. In general, the assumption that data are from an SRS, that one's really important. The assumptions are data, and it must be the population distribution is normal. The SRS is way more important. Sample size is less than 15. You can use the T procedures if the data are close to normal, or if the data is clearly non-normal or there's massive outliers, then you can't use T. But only if it's clearly non-normal. Sample size of 15, T procedures can be used except in the presence of outliers and very, very strong skewness. So this is somewhat close, not too bad. T procedures of 15 or more. If it's really bad, you can't use it. But if it's only sort of bad, they're fine. Over 40? Go ahead and use it if it's the worst distribution in the world, because the means will still normalize pretty well by the central limit theorem. So can we use T? Consider several of the data sets we graphed in chapter 1. Figure 11.9 is a histogram of states residents who are at least 65 years of age. We have the entire population of 50 states. We don't even need to look. So yes. This one, figure 11.9, has first lightning strike each day in Colorado, has 70 observations. I don't even need to look at the histogram. Good enough. You can use the T procedures. This shows the distribution of word lengths in Shakespeare's play. We aren't told how large the sample size is. You can use the T distribution for distribute if the sample size is roughly 40 or larger. This is pretty skewed. I would say you could use this at 20. It's not that nuts. It's not that ridiculously skewed. And it's not 20 words, it'd be 20 plays. Okay. Depends on the data for this. Percent of Shakespeare's words in several different plays. Or is it? Can use the T procedures like this sample size is roughly 40 or larger. Actually, I think it's 40 or larger, 40 or more words. So it probably should have multiple plays for this to be thing, but with Shakespeare's plays, yeah, that's kind of skewed. I would say you can do this at 30 or proceed with caution is probably a great ruse. We'll be cautious if we don't know, but so the power, remember power is 1 minus type 2 error. We talked about power in chapter 11. And type 2 error is the probability that it is enough difference that we should have concluded, but our data wasn't far enough away for us to conclude that H naught was wrong and we should have concluded HA. So the power of Spanish teachers. It is winter before the Summer Language Institute in exercise 11.13. The director, thinking ahead to report he must write, hopes that enrolling 20 teachers, I gotta go to the next scan, will enable him to be quite certain of detecting the average improvement of 2 points immediately missing. Listening score. Is this realistic? So we need to compute the power. He wants to know, he says 2 points is enough of a difference to make it worth it. This would be worth. So he wants to know 2 against the alternative, and he wants to know if 20 is enough people. We must have a rough guess of the size of sigma in order to compute the power. People planning a large study often run a small pilot study for this or other purposes. In this case, the listening score improvements from past summer languages institutes have had a sample deviation of about 3. So we can take sigma to be about 3 because that's what it's been in several previous ones. We're not going to run a pilot study for this because we've already done this and been able to get the data. So we need to write a rule for rejecting H naught in terms of X. The t-test with 20 observations, H naught at the 5% significance level. So essentially we're calculating hold on, my writing pad. Okay, so essentially we're calculating, here's 0. We're calculating over how far is this value in my actual thing. So 95% X bar. So I am looking at T. Looking at the upper 5%, so this is going to be 5%, 0.05, with values of 3. I can get that from the inverse T. That you'd have to use 0.95, but with degrees of freedom 19 because there's 20, and get this 1.729. So I take 1.729 to figure out what X is. My assumed for this one was 0 from you. That they don't, I assume that they don't improve. I want to test against to make sure they do improve. My S is 3 over square root of 20. X is going to be 1.729 times 3 over square root of 20. So I'm just going to multiply both sides by my denominator. And that gives me an X value of 1.16. Now my other curve, so that's less than 2, that's at least a good thing. My other curve here, the power one, is centered at 2, and I've got this 1.16 hanging out here. So I'm really looking for what's the probability here. And with a T, and I don't think you actually have to do T on your IB exam. They usually do it with binomial, which I'll show you binomial at a later date. I think binomial is the most likely. It's a little bit easier, but it's important to understand these because understanding that process. So we're looking at the probability that X is greater than this. And we will actually use a Z-chart for this. Or we'll use our Z distribution. So I'm going to do Z equals X in this case is 1.16. Okay, so I'm using my Z formula. (1.16 minus 2 over, we're still using 3 over square root of 20 here. And when we calculate that, so I'm going to take that to the calculator. I'm actually going to go here, menu, statistics, distributions. I'm going to use a normal CDF. My lower bound is going to be 1.16. My upper bound is going to be roughly infinity, so I'm just going to call it like something like that. 10,000, 100,000. My mean is 2. My sigma is 3 divided by square root of 20. And I get 0.89. The type 2 error, I did this, so I did the over part. I put my lower bound on here. The nice part with the calculator is you can put the lower bound right here and go this to it essentially infinity. If you had done the lower bound at negative infinity to 1.16, you'd get this, which would be the type 2 error. This outputted the power. I've got almost a power of 90%. I'm probably willing to accept that. Okay, my power being close to 90% means 90% of the time, if it's actually a difference of 2, my test will tell me that there was a difference. I think that's reasonably confident with a 5% level. So we're using, this would only happen by random chance 5% of the time, and 90% of the time, I'm going to get results that will tell me if the difference is 2 or more. That's pretty good test. This is probably plenty accurate. I think the director can go forward. That is the end of section 11.1.